Alrighty, last example. So in the previous problems, we calculated the Ka values. However, this time we're going to calculate pH values, which is actually a more useful measurement for us to have because we have indicators that can identify those values for us and pH meters, so on and so forth. So the problem example here is calculate the pH of a solution of 0.080 mole per liter methanoic acid, for which the pKa is 3.75 at 298 kelvins. So I'm at standard temperature and pressure. This is again 25 degrees Celsius, meaning I'm standard temperature and pressure. That means that that Kw value holds for 10 to the negative 14th. I don't have to worry about that at all. I'm going to do something first here. They told me that my pKa is 3.75. And that means I can get my Ka value by saying 10 to the negative 3.75. So my Ka value is going to be 10 raised to the negative 3.75, 1.78 times 10 to the negative 4th. And that's going to be moles per liter, just because I know it's a dissociation. I'm just going to leave that alone. I'm just going to leave that there for a second. Now I'm going to fill in my ice table. I initially have 0.080 moles per liter of my methanoic acid. I have no methanoate. I have no hydronium. I know equilibrium is going to have to shift to the right because I have none of these to start. I'm dissolving in water. I'm going to lose some X on the reactant side, and on my ice table I'm again not including the water. Water is a solvent, and solvents that are pure substances do not have a concentration. I'm going to gain an X here, gain an X here, all because we're in a 1 to 1 to 1 ratio. And so now I've got some expressions I can write. I can say 0.080 minus X, X, and X. Now, the goal here is to figure out X. If I figure out X, I'll know the concentrations of hydroniums. I can negative log that, and I can get the pH. But watch what happens when I set this thing up. I get 1.78 times 10 to the negative 4th equals, and then I've got concentrations of HCOO, concentrations of H3O plus, all over the concentration of HCOOH, filling in my values, 10 to the negative 4th equals X squared over 0.080 minus O minus X. And you're going to say to yourself, oh my gosh, I've got quite the quadratic equation problem, algebra problem to solve here in order to figure out what X is going to be. But this is where chemists are better than mathematicians, because chemists know that we are dealing with a weak acid. And we know that this value of X has to be incredibly small. So a very small amount of the hydrogens have dissociated from my methanoic acid to start. So this is what chemists do, and it's a dirty little trick, and you're going to love it. They say, oh, this is so small, it's insignificant. Let's just say that that is really close to 0. It's not mathematically correct, but that's what chemists do. And then we now have the expression where we have 1.78 times 10 to the negative 4th equals X squared over 0.080. And man, the math just got all of a sudden so much easier to do. Now, if you were a purist, and said, hey, we just really can't disregard that x, you have more right than ever to solve for x using quadratic equations, and you'll end up getting a number really close to what I'm about to solve for. So I'm going to solve for x here. You're going to rearrange this equation where x squared is going to be 1.78 times 10 to the negative fourth times 0.080. I'm going to put that into the calculator. 10 to the negative fourth. And then I'm going to times that by 0.080, like 8% of it. And then I'm going to, I might as well write that part out. I'll have x squared equals 1.42 times 10 to the negative fifth. I'm going to square root. And when I square root, I'm going to find that my x, the amount of hydroniums in the solution, is going to be 0.00377 moles per liter. So incredibly small, would it have actually been worth it to leave that x value in the denominator? So what I'm going to do here is I know that that value is going to be my concentration of hydroniums, which will indicate my pH. Go back up here and fill that in. 0.00377. And then I get to square root, or excuse me, not square root, negative log it, because I remember that pH is the negative log of the concentrations of hydroniums. So I've got the negative log of 0.00377. Put that into my calculator. Second answer. And I find that I've got a pH value of 2.42, which is indicative that I've got a fairly weak acid here. It's not a pH of 0 or 1. It's a fairly decent pH for a weak acid. Now I'm going to give you a spoiler alert. If you were to do this the long way, and if you have the time and energy and want to do that, and find that the x value in the denominator here is crucial, you would find that the pH is going to be 2.92. And you can argue, well, that's a big drastic difference in pH. We could go back to that 5% rule when we looked at the change in concentration versus the initial. And if we solve for that and find that that was over 5%, then we probably couldn't get rid of the x in the denominator. But in this particular case, we could. It is under 5%, and we're pretty much in the ballpark. In terms of that 5% rule, again, it's not something that IB assesses you on. It's something that they want you to keep in the back of your mind to remind you that we are always dealing with measurements. Measurements that can be accurate and precise, or may not be. So hopefully this makes a little bit of sense. I know it's a little jumbled. Let me know if you have any questions.